So hi everybody, right? I'm Denis, right? I work for Bloomberg, which has absolutely nothing to do with my talk, right? Which is titled Optimizing Generic Algorithms, all right? Before I kind of jump in, let's do a few disclaimers, right? I will mention a few projects. They don't really know I exist, right? I'm no way affiliated with any of them. What I know I have pieced together from the internet and from what I measured, right? So I might be wrong about things. Everything I will show is measured on one compiler, Clang 8, and one machine, right? I have done some measurements on different machines and compilers. I will tell you where I know it's important. Generally be beware of bugs and issues, right? And I tend to be opinionated, right? Sorry. It doesn't mean that I'm right and you're wrong, but just a fact for this talk. So I have a very specific goal. Like, let's say you have a component and you care about its performance and you benchmark, you profile, and in the end you find that something, that the reason why your component is not as fast as you would like it to be is something very general purpose, right? It can be a standard algorithm, which is what I'm going to use as examples. It can be JSON parsers, string utils, like something that is not built specifically for you, and you don't have a good visibility in all of the usage. And so the question is, what can you do if your performance is that sort of a bottleneck, is that sort of a component? Okay. Why it might be interesting to listen to me about this, right? Which is a reasonable question. So I have a couple of patches to leave C++ that landed, and much more that didn't. And most of them have to do with algorithm header. Like, all of them have to do with algorithm header. I've done a few interesting contributions in Chromium base library, which is their collection of general purpose utilities. And I do micro-benchmark algorithms quite a bit. Okay. So this is how the talk works, right? I have 4 parts to it. First, I'm going to very briefly talk about micro-benchmarking. I need to show you one thing that I don't see shown enough. And then we're going to do 3 algorithms: partition point, merge, and Stablesort. And the idea is that with each algorithm, I'm going to show an optimization. I'm going to discuss how you can measure it and how you can make sure that this is a good optimization, or like it's not really an optimization, right? And it's going to be more complex with each one. It requires more measurements and more thinking. All right? Okay. So micro-benchmarking. If you don't know anything about micro-benchmarking, watch Shedler-Caruth's talk, Tuning C++, Benchmarks, and CPUs and Compilers, right? Just basically hands-on shows how to use Google Benchmark and Perf and some other tools. Really nice. And same as Chandler, I use Google Benchmark. Like, it's a tool that is used by many people. It's kind of writing benchmarking libraries is hard, and they have done a really good job. And with this, let's jump into the biggest problem, at least for my money, of micro-benchmarking. So this is live demo, which is totally going to work, I'm sure. It takes a while. QuickBench takes a bit to load, and it's a bit more to load. Yes, thank you. So don't try to read the code, it's a bit much, but this is a benchmark for STD merge. And this is what I'm going to do. I'm going to take this benchmark, and I'm going to copy it, right? And I'm going to run it again, and then we'll wait, because again, this is QuickBench. Oh, no, it's cached. Fantastic. I get a 4.2 times difference result, right? 4.2 times difference. Who knows what the reason is? Perfect. So this is code alignment. I'm not a hardware guy, so I don't know all of the details, but this is how it's been explained to me. There are parts of your processes that really depend on the alignment of your code, right? One would be branch predictor that actually tries to predict, like this sometimes, based on the direct address on when you will jump, right? And so if you get multiple addresses on one cache line, on one aligned bit that it tries to predict, like you will get problems there. The other big one is DSB. DSB is a cache for decoded instructions. So like you get an instruction stream, it gets decoded, and it gets stored in the DSB. This is cache, right? And there are like very weird, very complicated rules that I'm pretty sure make sense, but not for me. And like, if you don't abide with them rules, your processor will have to decode your instructions on each iteration of the loop. And this is how it looks, right? Oh, bad news, right? We can see that it can be 4 times slower. Usually it's not that bad, but like 2 times, 1.5 times, easy, right? There is no known solution even for benchmarking for this. If you know one, or if you would know one, there is a Google benchmark issue that has been open for the last 2 years. And it happens in production code. Like, there is totally possibilities that your hot loop is actually significantly slower than it could have been. Like, this is one of the hardest problems in optimizers. Like, this is what they really try to solve now sometimes. It's hard. Like, good news. Like, I heard of people who say that they have seen like a 10 times difference. Had never been my experience, right? So usually, if you hit code alignment, it would be huge, right? And it tends to be very unstable. So you tweak your code a little bit, and it goes away. I had never been working on a project where it was important in production, so I don't know how to help you here. But I can help you with the benchmarks. Right, and first thing I do is I have one benchmark per binary. So I have like one loop essentially, right? What this gives me, if at least I modify some completely unrelated piece of code, my benchmark stays the same, right? Otherwise it can be unpleasant. And tweak your code, run for similar types. So in this case, I'm going to run for doubles, and let's hope this works. It takes a while to run. Yeah, so like the difference is noise. Went away, right? So use multiple different similar types with similar properties to test your algorithm. On Linux, there are tools. There was a talk yesterday. I don't remember the title, but they were talking about performance counters. There are performance counters for this. I'm not familiar with those. Like, I don't know how to use them, but they exist. Finally, there is a post by Denis Yaroshevskiy on code alignment issues where he goes in like a lot of details why this happens. Okay. And with this, I can go into the first algorithm. Actually, if you have like a really quick question, I can answer it now. Okay, awesome. Is everybody with? Okay. Can you make the phone bigger because we cannot see the there's a quick bench code. The quick bench code like really was like it was a benchmark for merge. Yeah. Yeah, I will like please let me know if this is an issue again. Okay. With this we can go in partition point, or more familiar to people it tends to be lower bound, like binary search. Right? So let's say we had on a mission to optimize binary search. We can try to start with something like this sort of list, like what affects performance of a binary search. And if I were to compile this list, it looks something like this. So range size, right? I can binary search 1,000 integers or 1,000,000 integers. Right? It's going to be different times. Which element are we looking for? So we're looking for the first element, for the fifth element, for the 50th element, like going to be different times. Not so much for binary search. But if you try to compare like different searches, that's going to be important. The price of the predicate, right? We compare strings, we compare ints, right? We compare like strings that differ in the very late or in the very beginning, because it's going to be different times. Distribution of data, same example, like strings, different in the beginning, different in the end, right? Non-template operations will loop, we divide by 2. I tend to think of iterators as non-template operations because A, they're dominated by pointers, and B, for most part, at least now, they have similar properties except for iteration speed. Like the reference is roughly the same speed, it's still it's a reference, right? Equality is roughly the same speed, right? So I tend to think of iterators as non-templated operations. And finally, cache locality of data, like binary search jump around, all right, it's going to be important, like whether is everything in cache or whether it's not. And the final thing is binary size. Like, I don't care that much about overall binary at the expense of the binary search. Like, making binary search smaller so your overall binary gets smaller doesn't seem like a good trade-off for me. But what I do care about is instruction cache spells. So let's say you have a binary search combined with something else. And so your binary search might become faster, but your overall bigger loops that you actually care about become slower because you encounter instruction cache spells. OK. So let's do this. Like, if we try to write benchmarks for all of this, first it's going to take us a while to just write these benchmarks. Then to make sure they're correct, it's going to be difficult. And then we have to run them, like, regularly. So benchmarks for this presentation takes 2 hours to run, right? If you're going to write more of those, you're going to make more time to run. Like, if you're Google, they have some magic CI people who can make this work for you. I'm not Google. I have to run my benchmarks myself. So I have to, like, prefer quality over quantity. And the way I think you can do that is to start with an optimization, right? So come up with an idea first of what do you want to do, and then try to benchmark it. First, like, pick 1 or 2 benchmarks that are, like, really fundamental for the algorithm. Like, this is what my algorithm does, right? Then, if you're optimizing, like, not the most general case, but something specific, let's say big types, or I don't know, add the benchmark for that. And finally, try to benchmark the things that could have been negatively affected. OK, so let's try and do that. Let's start with an optimization. OK, I'm going to make this bigger preemptively. Can you see it? No? OK. It's going to be bad if you can't see that. Sorry, but this is a middle point between first and last. So I have 2 iterators, first and last, right? And what I'm doing, I'm subtracting last from first and divide by 2 to find the middle point between 2. And I wrote this function. This is like roughly what happens in your binary search. Not exactly. But I looked at this function in Godbolt, and I saw this number. This is like a big, big number. You can see. There's a really big number. Right. And so what this number is, like, I did something, and this is like a negative number, actually. And so what happens here is that compiler cannot tell that last is always bigger than first. So it has to account for sign when it divides by 2. All right? So let's like not do that. We can do it in a couple of ways. The way I do this, and I'm going to call this function. If I could spell it would help. Almost there. Yeah. So in elements of programs, this function, programming this function is called half non-negative. And basically, there are 2 ways you can do it. You can do shift, which is what, for example, lib C++ does in MSVC. Or you can do cast on science. I chose cast on science. It gave me like slightly better code gen, right? So that's the idea for optimization. We got a smaller assembly, or we got a different code. OK. So let's analyze this. What did we affect, right? We affected only non-templated operations, like we divide by 2 differently. We don't do much else. We reduce the binary size by 2 instructions. But I claim if you reduce binary size, you're good, right? I don't know anything that you should care. Like, reducing binary size is good. I don't know why. Why would it be bad otherwise? Overall. OK. So let's come up with a basic binary search benchmark, right? I would claim that with whatever binary search you do, it's better binary search 1,000 integers really well, right? I plot all of my measurements, so I get to 1 parameter, right? Because I can do it on a plot. I chose the element to look up, right? So I look up first element, I look up 50th element, 5,000 element, you know. And finally, we need to double check for int64. I will double check for int64s and doubles to make sure that I don't run into code alignment issues. OK, let's look. So this is standard lower bound from libc++ on my machine. It's better now, right? And this is my lower bound in red, right? So I have, I would say, roughly 30% faster, right? For integers, and I can check for doubles. I almost can check for doubles. Would be nice if it loaded. No? You don't want to load? Oh, I didn't check that. It will work for just the doubles. OK, so this function has landed in libc++. This is now shipping with Clang. I wrote a nice, so I think we're done with binary search at this point, right? I wrote a binary post between linear and binary search some time ago, which explores some more stuff about binary search and compares to linear search. And I also, for the last committee meetings, I did some measurements comparing flat set and flat hash set from Upsale. And there were more measurements on binary search if you're interested. OK. And with this, I'm ready to jump into merge, unless somebody has a really quick question. OK?
Does that not get shipped with the GCC?
GCC uses a different standard library. They use Shift. So I compared against GCC. It's roughly the same thing for them.
So the API is available there too? API that you mentioned is available there too? You added some, I forgot the name of the API.
No, this is internal function. Sorry, this question is the function half non-negative available in GCC? Right? No, this is an internal function to the standard library. Right? It's a cast to unsigned and divide by 2. OK, merge. Right, holding time. OK. What affects performance of merge? Let's kind of do the same thing. OK, so I would say the total size of how many elements you merge will make a difference, like you merge a million elements or 10 elements. How elements are mixed. Like imagine you have all the elements from one range and all of the elements from the other range. Like it's going to be different if they're going to be very mixed. Like you're going to have different branches, prediction things, copy we're going to kick earlier and stuff. The price of comparison is going to be important, like again the same string thing. Right? A price of move or copy if you copy, right? Because you do moves and copies. Non-templated operations, again, will loop. Cache locality of data and binary size. Again, merge can be used in bigger loops. It's important for it to be reasonably small. OK. I'm really sorry for the people in the back. I can't do much here, right? I can do the best. But this is like merge that comes with libc++. All right, so what it does, first it checks both boundaries, like if one of the ranges is empty, right? And then it picks the smallest element, right? If the second range is smaller, we're going to take that. If the first range is smaller, we're going to take that. We're going to optimize this in 2 steps. Like the first thing I noticed here, right, is I noticed that we do 2 checks for conditions, while we only enhance only one element from the left range or from the right range. Makes a little bit of sense? It's really hard to tell. Right? So let's stop doing that. It's not a very interesting optimization, but it helps me build on it. Right? So I'm sorry. Yes, go-tos. Right? But this is basically what we're doing. So now, after we're advancing, we're doing the check. And we're doing while true, so we don't check in the middle. Yeah. Oh, we need to analyze how we did first, right? So what did we affect? Out of all that list, we affected only non-template operations, like we check the boundaries differently. And we increased the binary size by roughly 11 instructions for integers. We will deal with binary size later. But let's go into non-template operation. Let's do the basic measurements first. Basic merge benchmark. I would claim I would really like a merge to merge 2,000 integers really, really well. I get one parameter, and I'm going to parameterize on 2 sizes. So I have 2,000 of random integers. What I'm going to do, I'm going to split them into arrays, right? And what this gives me is actually, it gives me a representation of how the values are distributed relevant to each other. Like if you're going to have in one range, you're going to have 1,900 elements. And in another range, you're going to have 100. It means that from the bigger range, you're going to have large chunks of uninterrupted elements. Make sense? OK. And again, I'm going to double check for in64s and doubles. Let's see how we did. So this is standard merge. This is me. Who knows what's happening? I can have you a hint. So I'm not going to try to switch. It didn't work. But this is a performance for doubles. So for doubles, standard merge beats me to the extent. This is code alignment. Like, code alignment pops up all the time. All right, I mean it, watch out for it. It's really bad. But the same thing for in64s. Like, standard merge beats me, not as bad, but still. It wasn't a very interesting optimization. Let's look further. Like, let's look at our while loop. I would like to scroll it. Would be really nice. Awesome. So here's the problem. Like, when we take this element from the bottom branch, right, we need to do two jumps. We jump here in the if, and we jump here back to the beginning. For the first element, we don't do this jump, right? And as far as I know, not doing jumps is much better than doing jumps. There is one very popular technique to not do jumps. Who knows the technique? That's a good one. No, I'm talking unrolling. Like, so we can unroll. This is how I'm unrolling. Like, so I took this guy from the beginning, right? The one of the elements, and I'm gonna put it like again in the very below, right? In the very end. Like, this gives me an interesting properties to it, right? So I'm gonna show just one of them. This does less jumps, and here's, for example, why. So when I take this element from the second range, and I'm gonna do a condition, I'm gonna do one jump back here to the second range, right? So it's one jump for the element from the second range instead of two. Should work. Like, I'm gonna tell you at the beginning, it will work. The reason your compiler doesn't do this for you, it's really bad for the optimizers. But like, they don't understand. But okay, what did we affect, right? We have one extra comparison and one extra assignment. So our, how much we increase the size of the loop is going to depend on the type, which is difficult. We affected non-tablet operations, obviously. We loop differently, we jump differently. And we increase the binary size. Again, we're going to deal with binary size a bit later. But let's look at the basic benchmark. So this is comparing with standard for ints, but we know for ints there was a code alignment issue. So let's look for doubles, and I disabled my. This is for ints without standard merge. So for ints without standard merge, I am like have a really nice performance. But this is comparing with standard merge, right? So this one, the gray one, is a standard merge. This one is me. This is going to be about third faster. For int64s, it's not going to be, sorry, this is without my merge. For int64s, it's not going to be as good, right? But it's still a nice speed up. This is about, I don't remember how much. But, I think it's slightly less than a quarter. Okay. But we increase the binary size. Can you follow me more or less? Okay. It's just really hard. Okay. So we increase the binary size, and again, the idea with binary size increase that you have like some sort of bigger algorithms that depends on you, and that's gonna be slower. Does anybody know a good example of an algorithm that uses standard merge? Yeah, standard Stablesort. So that worked out really nicely, right? So basically, I would claim, if we plug in this merge into Stablesort and we see an improvement, then the merge was good. But before we do that, let's kind of deal with merge a bit. So this is my merge. Who knows what this is? On the sides, the giant drop. Any guesses? Yes, this is just copy. And copy compared to merge, remarkably, even compared to merge with one element is a huge difference for small enough ranges. So this is 2,000 elements, which is small, small enough that branch predictor doesn't seem to do anything. I have an algorithm that looks like this, so I'm going to disable one of those. There are two similar algorithms, right? So what it does, it's slower on average in the middle, but it's really fast, and when it gets to one element, it's going to be almost the same as copy, right? The effect is not so dramatic when you get to bigger ranges, but for smaller ranges, it's still important. For example, variation on this is really important to implement a good flat set for my money. Okay. So kind of, I claim we're done with merge before the binary size thing. There is a Denis Yaroshevskiy, again, post on branches, where he goes in a lot of details about branches. I tried to contribute this to libc++. It didn't land so far, but I talked to Marshall today. Maybe that will change. For the biased merge, it can behave different on different compilers. There's like trickery to it. And I have a similar algorithm that does deduplication, right? If you need that, talk to me. Okay, and with this, I can answer like a very short question on merge. No? Are you okay? This is really hot here. Okay, cool. Stablesort, right? What the hell is Stablesort, right? So Stablesort is a combination of 3 algorithms, typically, right? Well, it's a memory adaptive merge sort, right? It's under 8 elements in libc++, last I checked, unless I'm wrong, it's insertion sort. Then it goes into merge sort with a buffer, and then it's going to do the merge sort that I'm going to call rotating middles. It's not an official name by any means. Unfortunately, reality is, like, I don't believe this ever happens, but it has to be there. It's a weird situation. So, unlike my merge and my binary search, I don't have like a really solid stable sort. I implemented these 2 bits, right? That's out my stuff. So, like, I don't have, this is a bit shakier here. Okay. What affects performance of sort? Like, let's do the same thing. Let's see what affects performance of sorts. 1 million things, right? Total size. How sorted is data already, right? If you have almost sorted data, insertion sort going to be wonderful, right? If you have not so sorted data, not so wonderful. How many duplicates do we have, right? There is a famous quicksort bug where you don't separate duplicates into 2 groups, and then your performance suffers from that. The price of the comparison, the price of move, like how expensive it is to move things, the cost of non-tablet operations, also looping again, cache locality of data, and binary size. I would claim that for sort, like, first of all, sort is not going to be small, right? Like, no way. Like, and second, it's not going to be in line. Like, as far as I have seen, a stable sort at least never gets in line, right? And honestly, like, I think for stable sort, it's more okay to grow in size than, let's say, for binary search. Okay. Let's talk basic sort benchmark. Like, I'm absolutely doing the same thing. Like, we're gonna, yeah. I'm gonna sort 1,000 integers. Stable sort 1,000 integers, right? I'm gonna parameterize on how sorted the integers are. So I'm gonna go from sorted to like super shuffled to reverse sorted. Okay? I don't know how to do duplicates. There are some ideas that I have seen, but I don't know, like, oh, here's a number, now do different duplicates. That's a bit tricky. If you know how to do that, awesome. And again, we need to double check for code alignment. One last thing, this is just, they didn't come up in the previous examples, but often in benchmarks you have some sort of baseline, right? This is my setup code. You need to subtract that. Okay. So I needed to go from sorted to reverse sorted. I was like really smart. I went online and I found an algorithm to do lexicographical permutation. I give it a number and it gives me a lexicographical permutation from that number. And it's like, well, cool and all, but imagine this. You take the biggest number in your array. You put it first, right? As far as lexicographical permutations go, like, this is a really big lexicographical permutation, right? Almost at the end. But as far as, you know, almost sorted, 1 element out of place, I would bet, is almost sorted, right? So that didn't work. And the reason I'm telling you this is that benchmarks tend to be really, really error prone. Like, this has lived in my code for like months and a half. And I have routinely been wrong about benchmark data. So watch out for that. I don't have an answer, right? end up writing like a bias shuffle algorithm. So it's like similar to STD shuffle, but you give it a number, and it's like the probability within a certain range will be higher. So like your element is less likely to get far away, if the number is small enough. I wrote a bad one. If somebody knows how to do a good one, I would appreciate it. So okay, this is 2 of my stable sorts. Okay, so, and I just plugged in the merge I just showed you, right? And I'm faster by a third, right? If I'm gonna do doubles, it's still not gonna work. It works for doubles. I can do this. Right, so for doubles, it's a bit smaller, but still okay. If we're going to compare with standard sort, just out of interest, my stable sort is not that good, right? But I actually do like really well. I almost as fast as STD sort, and like my stable sort, and like a third faster than STD stable sort. This will go away if you go to the bigger sizes. They do other things that make it go away, but still, I was really proud of that. Okay. But we kind of said that we're going to have issues with bigger types. We're going to have issues with code alignment, right? So if we shove in bigger types, this should stop working. Can we do that? Well, let's try at least, right? So I have, the way I want to do this is I try some possible bigger types. Like the first one I'm trying is like a string. It's a fake URL. So I have HTTPS and then some sort of number and .com. So it's going to be a short string. And the thing is, what I like about it, it's not going to be a trivial comparison. So the comparisons is not going to differ in the first character. I use pairs of those to double check for code alignment and stuff. And another thing I use is a no-inline int, which is like an int wrapped in a struct where all operations are no-inline. It's a bit weird, but like no-inline move is generally a bad idea, but I have seen it happen. Like, okay, so let's have a look. Right, so for strings, my fancy optimization with merge didn't do anything. Right, and you're not going to work. Okay, so for pairs of strings, it's losing. So this is actually where we hit the problem. Right, it's losing not that much, but it's still bad. And for no-inline integers, I'm winning, but by a tiny, tiny margin. All right. So I think this is okay. Like integers or small types or primitive types, in my money, more important than big types, especially for things like sort, maybe. But can we do something for bigger types? Like, can we design specific optimization for a bigger type? I had an idea. Let's sort pointers. Right? So let's take pointers to every element in our array, sort them, and then rearrange the underlying array based on that. There's an Elements of Programming Chapter 10 rearrangements that talk about standard rotate for random access iterators, which explains like all the ideas you need to do this. Let's see if it makes sense. So this is it's going to be, I'm going to count the number of operations, right? In this case, I'm counting the number of moves, right? Everything else stays the same. The only thing that changed is I'm swapping pointers around, right? And then rearranging everything. So if you count the number of moves, I think 13 times better. Like, so I'm moving like roughly n elements instead of n log n swaps, which is nice. So maybe it should work. What did we affect, right? Well, obviously, the price of move is the first thing we kind of have to care for. All the non-template operations, like in many respects, like we did restructure of a loop and stuff, right? Cache locality of data, right? Now we compare through pointers into different places of the array, and so we might have a problem with cache locality, right? Because merge is very cache local, but when you do pointers, it's not. And we increase the binary size. But again, I don't care that much. So for strings, this optimization actually makes tiny little bit of sense. Oh no, sorry, the other way around. No, it doesn't. Like the green, the top one is. So for strings, it doesn't make any sense, right? For pairs of strings, it does make a little bit of sense here, right? So sorting pointers for like 1,000 strings, it kind of makes a little bit of sense. For no inline ints, it makes a lot of sense, right? So if you move with no inline, that might be a really nice trick to do. Let's look at cache size, though, right? So for cache size, in order to see cache size, we need to basically sort bigger arrays, right? Okay, so for strings, it didn't make sense and then never start making sense, right? For this is the same one, I'm sorry. For pairs of strings, right? This makes sense at 1,000 pairs of strings, but as soon as we go bigger, the cache effects start to kill us. For no-inline ins, this is a questionable benchmark because I can shove a lot of integers into a cache, and so it makes sense up to like 100,000 integers, but then it goes bad. Okay. Should we do it like in the, let's say, in the standard stable sort, right? We could check for no inline move, right? This can be an intrinsic or something, right? Move is always bigger than copy of bytes in one direction, like if you think about it. I could not actually make this one work. So I tried to like, well, let me try a bigger array. Just copying is really fast, but potentially it could be. Generally speaking, I need better implementations of everything involved to like really test, but I don't think this is like a good thing for a standard stable sort. But as a standalone tool, sorting pointers and then rearranging the original array based on pointers is really powerful. Because you can do things like sort by parallel array, right? You have an array of criteria and you can sort by it, which is really nice. Okay, I'm going to do conclusions at this point. Did I answer? Yeah. Okay. So how to optimize a generic component, right? What did we do in the end, right? We kind of compiled the list of everything that could affect our performance, right? We came up with some idea of what we can do to make it faster. We built benchmarks for the basic case. We built benchmarks for the specific case. And then we built benchmarks for what could have been negatively affected, right? And for all of these benchmarks, we, in the end, will make a decision like, is it a good optimization or not? Okay. Some general points, I would say. So if you take your specific code, you probably know minimum requirements for the machines. You know maybe your specific data or workflows. But if you're doing something like really general purpose, have some sort of rationale that doesn't come from plain measurements for why this is good. Like it can be as simple as like, we are doing less jumps. This is good, right? Or it can be some sort of mass boundaries or whatever. Benchmarks are very error prone. Multiple times I have stumbled upon it. Like my data wasn't right, my measurements weren't right. Small changes matter a lot. Like we did very tiny tweaks and it was like a 1/3 inch. If you want to take a crack at something, standard rotate would be a good candidate. There are two implementations, one in libc++ for random access rates, the other is in GCC. They are different. And you can, if you can come up with a general, one is better sometimes, the other is better sometimes else, right? If you can come up like, you know, this is how we actually do it, would be really cool. There were two things that helped, right, doing this. One is knowing a little bit about hardware and a little bit about tools, right? And there are multiple blogs, like people who like hardware, right? They have like Twitter that explodes with stuff. They have multiple blogs where they will go at length about different parts of processes. Really hard read, but they seem to like it. There is LLM conference where like sometimes they discuss like related to hardware stuff, and this is really close to us, which helps. Not a lot of people. Matt Godbolt or Niall Douglas, by Google for their talks, fantastic, dives into some hardware stuff. The other part of it was learning a little bit about algorithms, right? So knowing how to do standard rotate for random access helped do the pointer rearranging. Well, first off, there is Alexander Stepanov's courses on A9, which are fantastic. And there is EOP, but EOP is hard. This is much easier. Alexander Stepanov is a really solid lecturer, and it's really nice. Helped me a lot. There is competitive coding. There is Connor's code report, which has sometimes really nice algorithms into it, and it's modern C++. There is stuff like Geeks for Geeks. Your eyes tears up a little bit, but they have really good algorithms. And finally, I know this is an Andrescu talk, but it's not a very known one. There is Treasure Everywhere, where he talks about how to implement partition really fast. And this is really cool. Right? And there was Keynote from the CVPCon, also on similar subjects. I tried to do some university courses online. There are a lot of those. I am not smart enough and not... Okay. Thanks to Oleg Fatiev for reviewing some of the stuff, and to Denis Bahwala for answering some of my questions. And I have time for questions. I have probably a lot of time for questions. What's it going here?
Thank you for a great talk. So as a compiler engineer, what usually makes me really worried is that when people are optimizing their code, they're making assumptions like, oh, this loop, you will have a jump here, or this goto will turn into a jump here, you will have a memory load, etc. In C++, we are not programming against hardware. We are really programming against the abstract machine and the as-if rule, like everybody knows, right? So what are your thoughts on that?
Sure. So that's all very true. Yes, compilers smarten you unless you are really measuring. I claim that I'm measuring, right? So actually, I had one of the worst experiences I had with this type of stuff is trying to beat compiler over the head to do the assembly I want to do. Right? You're like, let me do a switch. Nope. Let me do rotate the ifs. Nope. Let me do big aspect. So when you do this stuff, you look at assembly and you decide from there. You don't do from the code itself. Right? In this example, just the code matches what is in assembly. That's
in an algorithm like merge, the requirements for it, I think it has to be a merge. Your iterators are merge iterators, which I guess I don't remember, but they're something like they're input iterators plus there's a comparison. But as you say, very, very often your iterators are in reality random access iterators. They're wrapped pointers. And the standard libraries generally don't kind of specialize for this, but could you write specialized algorithms like a faster merge that works only for random access iterators, for example?
I'm fairly certain standard library does a lot of that. So yes, you can specialize for random access iterators. For merge, I do not know why that would help you. The only thing I was thinking about was, hey, I have, n number of integers. I can pre-compute the size and maybe figure out from that one size instead of doing two sizes. I couldn't figure out how to do that, and I don't think it's possible. But standard library does a lot of that. Again, rotate has free implementations. Right. I don't know, is it specific? They also do things like, for example, copy will be optimized to memmove, right? Sure. By the standard library, not by the compiler. Right. And so I wanted to show you, this is actually the code that I built for this. It's turned out to be really nice. This is just the size of the README. Sorry, oh, it's not me. Okay. Yeah, there's a lot of interesting things. For example, recently we tried to do a uint tuple where you pack a bunch of integers into a tuple, which gives you like we wanted to do better comparison, right? So you can compare like, multiple tuples with one comparison. Actually, I can show you this. I have measurements here. Almost here. It would be nice if it loaded. Would really appreciate it. Any other questions?
Hi, thanks for the talk. I'm sorry, this is not the right question, but you had a question, or you said that you don't know how to deal with this code alignment issue.
Yeah.
So just two notes on that. There are some performance counters in perf that can be used to measure it. And there is a tool called Stabilizer by Emery Berger. And it basically tries to compile the binary in a lot of different permutations so that it tries to put the functions on different places. And therefore, it checks whether a change you made, for example, to std merge, is faster only by accident because you got better alignment, or whether it statistically is faster. So there are some tools for that.
So can I tell it like this is the functions that I'm trying to optimize? Like,
I'm not sure if you give it specific functions or just tries to permute like all functions in a binary, but it was designed for this specific use case because sometimes you make a change and it's faster, and then you kind of discover that if you add another function on top of it, it will be slower again because it will be aligned differently. So yeah, this is a real concern. I think that when you benchmark, you have to make sure that it wasn't a random effect that you are suddenly faster.
Cool. I didn't know that. Thank you. So yeah, this is the sorting. Oh, come on. So if you have, let's say you have a pairs of 64-bit integers, right? And you so this is std sort for pairs of integers, and there's std sort if you pack those 64-bit integers into one 128-bit integer, right? It's going to be third faster on the it's a similar benchmark that I showed previously. Right? Alek Fatiev did the work for this. Like, really nice. So if you actually have a sort that sorts by multiple integers, consider packing them into one.
I have another question regarding the error-prone benchmarks. How do you go on about, if you say they're error-prone, how do you go on about finding the error in it? What would be your strategy to find if they're correct or not?
If I had a good answer for that. So for everything I showed here, I actually had like multiple different sets just written in different times. Some of them were submitted to the review, for example, for libc++, other people looked at it, right? At some point I tried printing out data. Like obviously you try to run some tests, right, for the benchmark generation stuff. But like I want it to be random shuffled. Can I write a test for that? So good question. Like looks random shuffled, doesn't look random shuffled. I don't know. Okay. Thanks everybody.